We'll start in 1 minute. This week we will review for the final exam each day. The final exam will be on Monday, May 3rd from 10 a.m. to 12 p.m. Mountain Standard Time, and it will be Zoom proctored. Okay, the first page, another statement about when the final exam is. On Monday, May 3rd from 10 a.m. to 12 a.m. 12 p.m. And the final exam will be Zoom proctored the same way the other tests were proctored. One difference, you can use a paper sheet of handwritten notes on the front and on the back, and the dimensions of the paper should not exceed 8.5 inches by 11 inches. Something else you can do to help prepare for the final exam is to review the tests 1, 2, 3, and 4. And as time permits, you can also look over the test review sheets. So we'll do a few examples that we encountered throughout the semester. The integration by parts formula. If you have an integral of the form u dv, then the integral is u times v minus the integral of v du. So let's use integration by parts. In this example, the integrand is 2x times e to the 3x. So if we pick u to be 2x, then du is just 2 times dx. And pick dv to be e to the 3x dx. And then v is the antiderivative of e to the 3x, which is 1/3 e to the 3x. Then apply the integration by parts formula. So u times v, 2x times 1/3 e to the 3x. I'll write that as 2/3 x times e to the 3x. And then we subtract v du. So, sorry, we subtract the integral of v du. So we have a constant 2 times 1/3. I'll put the 2/3 out front. And then the radicand, or the radical, sorry, the integrand is e to the 3x dx. Okay, then one more step. 2/3 x e to the 3x. And then minus 2/3. An antiderivative of e to the 3x is 1/3 e to the 3x. And then we include the constant of integration. And we can simplify a little bit more. So the next step, 2/3 times x e to the 3x minus 2/9 times e to the 3x plus constant. If you need to practice integration by parts more, make sure that you get sufficient practice. Also review the trigonometric integrals. We'll review just a few of some of the common examples, but don't limit your study to the ones that you see here. So review the basic derivative and anti-derivative formulas and identities for trigonometric functions. Okay, the first example, integrate sine of 2x. One way to do this, using the substitution rule, we can just write down an antiderivative by writing 1/2 times cosine of 2x, oops, negative 1/2 times cosine of 2x plus a constant. So the antiderivative has to be negative 1/2 cosine of 2x, because when you compute the derivative of negative 1/2 cosine of 2x, you get the negative of a negative sine of 2x. So you can do that in one step. Another option, an identity for sine of 2x. All right. The identity, even if you don't want to do it for this integral, this identity, sine of 2x, is a nice identity to remember. Sine of 2x is 2 times sine of x times cosine of x. So if you use that for this, we have the integral of 2 times sine of x cosine of x dx. And one reason for picking this is if we use the substitution rule, pick u to be 2 times, well, just pick u to be sine of x, then du is cosine of x dx. So an antiderivative of this is 2 times sine of x squared divided by 2 plus a constant, or just sine of x squared plus a constant. The fact that both of those are antiderivatives shouldn't be a surprise. I'll point out why in a minute if you don't recall. The next one, the antiderivative of cosine of x squared. Well, I always seem to use the same identity for cosine of x squared when I need to integrate it, and that is cosine of x squared is equal to 1/2 plus 1/2 times cosine of 2x. And then we can find the antiderivatives of those easily enough. An antiderivative of 1/2 with respect to x is 1/2 x. And then an antiderivative of 1/2 cosine of 2x is 1/2 times 1/2. I'll just write it as 1/4 times sine of 2x, and then plus a constant. In a similar sort of way, to find the indefinite integral of sine of x squared dx, we can replace sine of x squared with 1/2 minus 1/2 cosine of 2x. Okay, then an antiderivative of this is 1/2 x and minus 1/2 times 1/2, or minus 1/4 times sine of 2x. Okay, earlier I mentioned these two antiderivatives of the same function. One is negative 1/2 times cosine of 2x plus a constant. And the other one is sine of x squared plus a constant. So using this identity, we see that sine of x squared differs from negative 1/2 cosine of 2x by a constant. Okay, moving on to the next example. The indefinite integral of tangent of x to the 5th times secant of x to the 2nd dx. So here, the thing that stands out to me the most is to note that the derivative of tangent of x is secant of x squared. So using the substitution rule, if we pick u to be tangent of x, then du is secant of x squared dx. And then substitute, replace tangent of x to the 5th with u to the 5th, and replace secant of x squared dx with du. And then the indefinite integral of u to the 5th du is u to the 6th over 6 plus a constant. And then the last thing we do, replace u with tangent of x, so we get tangent of x to the 6th divided by 6 plus a constant is the indefinite integral. Okay, so like I said, review as many of the basic derivative and antiderivative formulas for the sine functions or the trigonometric functions, and also review some of the important identities. And then there is trigonometric substitution. So for this indefinite integral, 1 over a squared plus x squared dx, since we have a squared plus x squared, we can pick x to be a times tangent of a different variable than x. So I'll just pick theta. So when you make this trig substitution, make sure the variable you pick for the trig function is different than the variable that you're setting it equal to. Okay, so if x equals a times tangent of theta, dx is equal to a times secant of theta squared d theta. And also a to the 2nd plus x to the 2nd is a to the 2nd plus a to the 2nd times tangent of theta to the 2nd. If we factor a to the 2nd out, we get a to the 2nd times the quantity 1 plus tangent of theta squared. And then remember that 1 plus tangent of theta squared is equal to secant of theta squared. So that is, we just used one of the Pythagorean identities. 1 plus tangent of theta squared equals secant of theta squared. Okay, so we make substitutions into the integral. Dx, we can put that in the numerator. So dx is a times secant of theta squared d theta. And in place of a to the second plus x to the second, we can just replace it with a to the second times secant of theta squared. So a to the second times secant of theta squared. Simplify the integrand. A over a to the second is 1 over a. Since it's a constant, I'll put it on the outside of the integral. So 1 over a times d theta. So we get 1 over a times theta plus a constant. And then we're going to use our trigonometric substitution to replace theta with an expression in terms of x. So now we focus on the assignment x equals a times tangent of theta. So x over a equals tangent of theta. And then the inverse tangent of x over a equals theta. So that's all we have to do now, replace theta with inverse tangent of x over a. And our answer is 1 over a times inverse tangent of x over a plus constant. Okay, the next one, the indefinite integral of the square root of a to the second minus x to the second dx. For the case of a squared minus x squared, picking x to be a times sine of theta is the one that is normally picked. It would be possible to use x equals a times cosine of theta, but I suspect one reason that that is not chosen most of the time is because it introduces a negative sign in the eventual process. And so avoiding negative signs is probably why x equals a times sine of theta is picked. Because dx is just a times cosine of theta d theta, no negative sign. Okay, then a to the second minus x to the second is a to the second minus a to the second times sine of theta to the second. If you factor a to the second out, we get a to the second times 1 minus sine of theta squared. And then using another Pythagorean identity, 1 minus sine of theta squared is just cosine of theta squared. So we get a to the second times cosine of theta squared. Okay, now we make substitutions. We have the square root. Instead of a squared minus x squared, we're going to replace it with a to the second times cosine of theta squared. And then don't forget dx. Dx is a times cosine of theta d theta. So in the next step, I'll do a couple of things. When we simplify the square root of a to the second times cosine of theta squared, we get a times cosine of theta. And then when we multiply a times cosine of theta times a times cosine of theta, we get a to the second times cosine of theta squared. And then we'll use the identity that we already saw today for cosine of theta squared. I'll bring the constant a to the second out front. And then we replace cosine of theta squared with 1/2 plus 1/2 times cosine of 2 theta d theta. And then compute the antiderivatives. Antiderivative of 1/2 is 1/2 theta. And then an antiderivative of 1/2 times cosine of 2 theta is 1/2 times 1/2, or 1/4 times sine of 2 theta plus a constant. Well, we're not done. We have to express all of this in terms of x. So we have to replace theta with something that involves inverse sine. And we also have to replace sine of 2 theta. Okay, let's work on theta first. Up here, here is our trigonometric substitution. X equals a times sine of theta. So if we solve this for theta, first divide by a, x over a equals sine of theta. And then inverse sine of x over a equals theta. So this is what we'll replace theta with in a minute. And then the sine of 2 theta. So let's use the identity sine of 2 theta equals 2 times sine of theta times cosine of theta. And then we multiply that by 1/4 times 2 times sine of theta cosine of theta. This will become 1/2 sine of theta cosine of theta. And then once again, we're going to use the trigonometric substitution to help us. Now we know that sine of theta is x over a, but we have to come up with an expression for cosine of theta. So we can do some right triangle work over here. If theta is the angle, and if sine of theta is x over a, then using the Pythagorean theorem, the adjacent side to angle theta is the square root of a squared minus x squared. And so cosine of theta is the square root of a squared minus x squared over a. So theta is x over, or sine, the inverse sine of x over a. So this is 1/2 times the inverse sine of x over a. And then plus 1/2 times sine of theta times cosine of theta. So plus 1/2. And then sine of theta is just x over a. And cosine of theta is the square root of a squared minus x squared over a. Oops, a squared minus x squared. over A. So let me know if you can't read that, but this is a good enough answer for what we want right now. Okay, the next example, the indefinite integral of dx over the square root of x squared minus a squared. So this time the trigonometric substitution that we want for x is a times secant of theta. And so dx is a times secant of theta tangent of theta d theta. And then x squared minus a squared is a squared times secant of theta squared minus a squared. Factor a squared out, we get a squared times secant of theta squared minus 1. And then secant of theta squared minus 1 is just equal to tangent of theta squared. So this is equal to a squared times tangent of theta squared. And now we go back to the integral and make those substitutions. We can put dx equals a times secant of theta tangent of theta d theta all in the numerator. And in the denominator, we have the square root of a to the second times tangent of theta to the second. So when we take the square root of that, we're just left with a times tangent of theta. Well, we get some cancellations. Tangent of theta divided by tangent of theta equals 1, and a divided by a equals 1. So we end up with the indefinite integral of secant of theta d theta. So you'll remember that the antiderivative for secant of theta is the natural log of the absolute value of secant of theta plus tangent of theta. We have to replace secant of theta and tangent of theta with expressions in terms of x. So the trigonometric substitution used is what determines that. So if x equals a times secant of theta, then x divided by a equals secant of theta. Then we can use a right triangle to help us find tangent of theta. So if theta is this angle, and secant of theta is x over a, then that means the hypotenuse is x, and the adjacent side is a. And the opposite side, using the Pythagorean theorem, is the square root of x squared minus a squared. So now we can write the natural log of secant of theta is x over a, and then plus the tangent of theta, which is opposite over adjacent. That's the square root of x squared minus a squared over a. and then plus the constant of integration. We could do a little more simplifying, but this is a good enough answer. Okay, got everything. Okay, we'll move on to the next sheet. Integration of rational functions by partial fractions. So in this first part, it says find the form of the partial fraction expansion, but don't find the constants. So note that in the denominator, the degree of the polynomial in the denominator is degree 8. When we square x squared plus 9, we'll get a degree 4 polynomial. And then when we raise 4x minus 1 to the fourth, we get another degree 4 polynomial. So altogether, the denominator is degree 8. And the numerator is degree 6. So just a reminder, if the degree of the numerator is bigger than the degree of the denominator, when integrating, then you should divide the numerator by the denominator first. But we don't have to do that because in this case, the degree of the denominator is bigger than the degree of the denominator. The degree of the denominator is bigger than the degree of the numerator. One of the factors in the denominator, x squared plus 9, that's an irreducible quadratic factor. So in the partial fraction decomposition, we write ax plus b over x squared plus 9. And since we have another factor, x squared plus 9 quantity squared, we have to write another one, cx plus d over the quantity x squared plus 9 to the second. The other entity in the denominator, we have a linear factor of 4x minus 1 to the fourth. So in the partial fraction decomposition, we'll need 4 rational expressions. One will be e over 4x minus 1, and then plus f over the quantity 4x minus 1 to the second, and then plus g over 4x minus 1 to the third, and then just one more, h over 4x minus 1 to the fourth. So you're probably thinking, why didn't I just write this where I had more space? And the answer is, I don't know. Okay, in the next part, evaluate this integral, 5x over x squared plus 5x plus 6. We can factor the denominator. So we'll rewrite this as the indefinite integral of 5x over x plus 2 times x plus 3. So we'll find the partial fraction decomposition of this, of the integrand. So the two factors in the denominator are just linear factors. So we can write a over x plus 2 plus b over x plus 3. And then with a common denominator, we'll get ax plus 3a plus bx plus 2b all over x plus 2 times x plus 3. The numerator of the integrand is 5x. So that means ax plus bx has to equal 5x. So if we take the variable out, this just means a plus b has to equal 5. And in the original numerator of the integrand, the constant is 0. In this expansion, the constant is plus 3a plus 2b. So 3a plus 2b equals 0. So now we have an algebra problem. Solve this system of two linear equations for a and b. So one way to do it, we can multiply every term on both sides of the top equation by -2. So we get -2a minus 2b equals -10. And leave the other equation exactly the same. 3a plus 2b equals 0. And then when we add these two equations together, on the left, the only thing that survives is a, and on the right-hand side, -10. So a is equal to -10. And then to find b, we have two options. We'll just use a plus b equals 5, or -10 plus b equals 5. So b is equal to 15. So in using partial fractions, the integral of the 5x over x squared plus 5x plus 6 dx, that's the same as the integral of -10 over x plus 2 plus 15 over x plus 3 dx. And this is pretty simple to solve. So an antiderivative of -10 over x plus 2 is -10 times the natural log of the absolute value of x plus 2. And then plus 15 times the natural log of the absolute value of x plus 3 plus a constant. So that's all there is to that one. Okay, the next topic, approximate integration. So we're going to just focus on the trapezoidal rule and Simpson's rule. So a reminder, the trapezoidal rule is a method for approximating a definite integral of a function f of x. So the definite integral of f of x from a to b can be approximated by a trapezoid. T sub n, here's the formula, delta x divided by 2 multiplied by the quantity f of x sub 0 plus 2 times f of x sub 1. So the to the right of the first term and to the left of the last term, all of the coefficients are 2. So coefficients of 2. And then delta x is b minus a divided by n, where n is the number of subintervals. When using Simpson's rule, the number of subintervals must be even. So n must be an even positive integer. So when we approximate the definite integral of f of x from a to b using Simpson's rule, then outside we have delta x divided by 3. And inside the brackets, the coefficient of the first term is 1 and the coefficient of the last term is 1. But in between the first and last, the coefficients alternate 4, 2, 4, 2, and so on. Okay, let's do an example involving the trapezoidal rule and Simpson's rule. So use the trapezoidal rule and Simpson's rule with n equals 4 to estimate the definite integral of x to the 4th dx from 0 to 8. Since it's pretty easy to evaluate this definite integral exactly, but that will be able to give you an idea of how close the trapezoidal rule and the Simpson's rule are in approximating it for a pretty small number, n equals 4. Okay, so first, I guess we create a table of inputs and outputs. The length of the interval is 8, from 0 to 8, and the number of subintervals is 4. So the length of each subinterval is 2. So we start at x equals 0, and then length 2 after that. So 0, 2, 4, 6, and 8. And then find the outputs that correspond to those inputs. So f of x is equal to x to the 4th. So when x is 0, 0 to the 4th is 0. When x is 2, 2 to the 4th is 16. When x is 4, 4 to the 4th is 256. 6 to the 4th, 6 times 6 is 36, times 6 is 216. 216 times 6 is 1296. And then when x is 8, 8 to the 4th, that's the same as 2 to the 3rd to the 4th, or 2 to the 12th. We know that 2 to the 10th is 1024, so 2 to the 11th is 2048, and 2 to the 12th is 4096. Okay, then the trapezoidal approximation for n equals 4. Let's see, what's delta x? 8 minus 0 divided by 4, or 2. So the number out front in the trapezoidal rule is delta x over 2. So I'll just write 2 over 2. And then the first term, 0. And then plus 2 times the outputs, the intermediate or the interior outputs. So 0 plus 2 times 16 plus 2 times 256 plus 2 times 1296 and then 1 time plus 1 times 4,096. Okay, I'll leave that for you to do, that arithmetic. Then the Simpson's approximation. So out front, it's delta x over 3. Delta x is 2, so 2 over 3. And then times the first output, 0. Then plus 4 times the second output, plus 2 times the third output, plus 4 times the second to the last output, and then plus 1 times the last output. Okay, let's get started on the next topic, improper integrals. This is one of the types of improper integrals. I'll just jot down other types of improper integrals. You could have an integral from negative infinity to infinity. Or from negative infinity to a finite number, whatever that finite number is. Let's see, you could have something like something from a to b, and if you have a factor in the denominator of x minus b, then this is improper because the integrand is undefined when x is b, and so on. But let's look at this one. This says use the comparison theorem to determine if the following improper integrals converge or diverge. Well, with some experience, you can get an idea of, you can have a suspicion on whether an improper integral will converge or not. But if you don't have that, it might take 2 or 3 or 4 efforts or attempts to actually come up with something that works. But I suspect that this one converges. So if I'm required to use the comparison theorem, then I'll start out this way. For x greater than or equal to 1, we know that's true because the lower limit, the lower x value is 1 on the integral. And I know that for x greater than or equal to 1, x to the second is greater than or equal to x. And if I take the negative of both sides, then negative x squared is less than or equal to negative x. Since the function e to a variable is increasing, then we know that e to the negative x squared is less than or equal to e to the negative x. So that would have to mean that the improper integral of e to the negative x squared is less than or equal to the improper integral of e to the negative x dx. So I'm going to compare the original indefinite or improper integral with the improper integral from 1 to infinity of e to the negative x dx. So if I can show that this one converges, then by comparison, this one also converges. So we have about a minute. We can evaluate this improper integral from 1 to infinity, e to the negative x dx. We write this as the limit as b goes to infinity of 1 to b of e to the negative x dx. And then an antiderivative of e to the negative x is negative e to the negative x. We evaluate this from 1 to b. Okay, so we get negative e to the negative b, negative e to the negative b, minus a negative plus, which is plus e to the negative 1. But as b goes to infinity, e to the negative b goes to 0. And so this limit is e to the negative 1 or 1 over e. So we get convergence. Okay, we're out of time for today. We'll pick up from here tomorrow. So go ahead and sign in for attendance.